Hello, welcome to the show. And this talk is going to be about some tracing and monitoring of Android applications. And as far as I know, there has been a lot of discussion regarding this kind of topic. And we opted to choose a kind of different approach than usual. And you will see this a little bit later on. A couple of words. We test pens for Deloitte. Me and Gergő as an intern, and I as someone who tells him what to do. And once upon a time, the beginning of this story finds two very busy and exhausted pen testers sitting in a very dark room and trying to do lots of Android penetration tests. And these applications involved lots of crypto stuff, bad crypto, and we wanted to find out where the bugs are. And as it turned out, most of our time was spent trying to figure out which classes do certain stuff in Android applications. I mean, we were trying to find the exact methods and exact classes which were responsible for certificate management, certificate pinning, login mechanisms, encryption, storage management, blah, 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 and this kind of stuff. And as it turned out, most of the Android penetration tests we were struggling to find our way around in massively obfuscated, hopelessly undocumented and unknown Android code. And as a bonus, we didn't have too much time to do this, so we wanted to find a way how to do this in a more efficient manner. And what were our options? First, the naive way was we took the APK, the installer of the application, we converted it to jar, used JED or JD GUI to get kind of exact representation. In fact, it's an approximation of the Java code within. And we were trying to find our way in a massive, undocumented, obfuscated code base, which took most of the time. That was a pain in the ass. And we opted for a little bit advanced approach, took the APK, used a static analyzer framework to pinpoint interesting stuff within. Who has ever used Androlyze? No one. Cool. So Androlyze is a static analyzer framework. You give an APK to it. It performs some magic autopsy on the contents and pinpoints you which classes and which methods do interesting stuff. I mean, where do SSL-related things implemented? Where's in case it uses some SQL cipher in the backend, then it tells you which methods and which classes use those methods. But in the end of the day, you try to find your way around in a massively undocumented, hopelessly obfuscated Java code base, which is, again, it's a pain in the ass. Static analysis sucks. Let's go for dynamic. We enable debugging in an application. We changed the manifest XML. We changed the debugging bit to true. Repackaged the application. Resigned the whole thing. Install on our test device. Fire up GDB, Dalvik debug monitor, JDB, and then what? You sit in front of a JDB console and try to find your way around in an undocumented, obfuscated, massive code base, which, again, is a pain in the ass. Let's go for something even more advanced. If we go for mobileSubstrate, mobileSubstrate is a very nice framework. It allows you to install a tool which hooks into API calls, and OS API calls, and processes the originator of the calls and allows you to overwrite the contents and to do many kind of stuff. This is very widespread and common in iOS world, but it still can be done in Android. Such tool is like IntroSpy is a very nice one. It's modular. It can be expanded, extended. It's very useful. So you have to define the scope, which API calls you want to hook, and you smile because you have a sensation of success as you monitor that, cool, the application does, okay, now it reaches Java crypto, it reaches for the default certificate store and this kind of things. But at the end of the day, you will find yourself in front of Eclipse, trying to find your way around in an undocumented, massive, obfuscated Java code base, which is still a pain in the ass. So would it be not awesome if penetration, we wanted to find a new way to overcome this kind of problems. So we wanted to do kind of like Chuck Norris, so that he stares at the code and irrelevant parts highlight themselves. So by magic. So we didn't want to pinpoint, manually inspect codes and the Java source. We wanted to make this kind of automatable. And it would be also awesome if the internal calls of the applications were also recorded, because there are many, many things going on under the hood. I mean, if we see an API call, then there must be something originating from. So we wanted to also get an information about those internal calls. And as a bonus, if this whole operation were permanent, I mean, there would be no need to start the application in a debugger or to use some fancy static analyzer framework. It would be awesome. So we wanted to go for this kind of permanent operation. So this is the point where we came up with the basic idea of deLogger. This was like help in the first time for ourselves. We wanted to make our work much quicker and much easier. So deLogger, as it is today, it's a full-blown Smali transformation engine. We wrote it in Python, so it can be expanded, modified. And what it does in this current scenario, it decompresses the APK first, which is the installer of the application, and choose the Smali log, the Smali code base, which is changed so that we log every function name, every invoke, every input parameter, and whenever a function returns, we make a log entry about that return and the return parameter also. And in the end, we repack the whole application again so that these changes are permanent, and it can be installed either on a device or on an emulator or anything else. So the basic idea of this application, I'm not sure if you guys can read it. Who can't read it? Okay, so I presume you can. So the thing is, anyone who's done any programming, I'm pretty sure this is called the hello, I am here kind of debugging. So we pinpoint this system out println, I'm not sure if you can see the cursor, but we pinpoint these lines into random bits of the code so that when the application is running, we see that, okay, this point is reached. So this is some very, very basic, one of the most naive way of debugging. And we chose this option, this way to follow, as you will see a little bit later on. So we talked extensively about options, how to monitor Android applications. And we had a word about the mobileSubstrate framework. And this is an interesting thing because mobileSubstrate hooking, it mainly focuses on interaction between the operating system and the application. So whenever a mobileSubstrate hooking mechanism is defined for a specific OS API call, then it intercepts these interactions between the OS and the Android application. And the bad thing is that if we have a big application with lots of crypto, lots of custom stuff, then it's only the tip of the iceberg, what happens between the OS and the application. So the point is, even though we have a very nice SQLite database in case of IntroSpy about the interaction between the OS and the application, we still have no idea about what's going on within the application, because that still handles the application as a black box unit, because it doesn't it doesn't change the application or doesn't have any influence on the application whatsoever. And that's one of the main advantages of the mobileSubstrate kind of approach, so that you don't have to tweak with the application, you don't have to change it, you don't have to resign the application. And this can come very handy because our approach of modifying the Smali code and resigning the resulting application again, it cannot be applied in every case. I mean, there are some MDM solutions or encryption applications and kind of some voice over IP applications also apply some self-checks. So if the signer entity of the application is not as expected, then the application exits. But if we change the application, change the Dalvik code and resign the application, then we will fail those checks also. So that's a main difference between the two approaches. So deLogger focuses on the internals of the application, and but you will see later on that this is not entirely true, so that we can monitor when the application reaches to the OS, but apart from logging it, we cannot intercept or intervene in any way. So this is only tracing and monitoring method. Okay, and let's see how this thing works together, and I hand over to.
One more for you, I think. There's one more for you.
Oh yeah, sorry. Oh, that's still me. So how this application works together. So deLogger is the white rectangle on this figure. The input is the installer of the application, which can originate from the Play Store, or come from the device itself, or can be distributed in a different channel. It doesn't really matter. What matters is we have an installer for the application, and we simply take APK tool, which is a known utility and pretty widely used when hacking Android applications. And we use that APK tool to turn this APK to Smali, which is an equivalent of, which is practically the bytecode that the Dalvik engine parses and runs. Then it's basically only like text files, so it's nothing very serious. You don't have to use IDEPRO or any kind of hex editor or debugger for that. And once we have a massive amount of text files, we use some magic, which will be explained a little bit later on. And this magic does the modifications we described earlier. So it inserts this kind of system out println kinds of statements into the Smali code itself. And the resulting Smali is re-signed with, repackaged with the APK tool. And we have to re-sign the whole application, because obviously the change of the Smali code, it changes the signature on the classes.dex file in the APK package. And once we have a modified signature, we have a fancy portable APK, which from a functionality point of view is pretty much the same as the original application, but we added some extra info into it. So that means we can install it to either on an emulator or a device itself, and once we start the application in the device itself, and we see the system logs with logcat, then we also see lots and lots of output. You will see it later on in the demo section. So what's cool about this thing is that how do we use this tool? We use it like this. We have let's say we have an application which uses some custom crypto. And that there's a login screen, and we want to know what happens when I press OK on the login screen. We process the application installer with deLogger. We install it on a device. We take it to the point where we enter the password. We clear the log, enter the password, press OK. Lots and lots and lots of entries are dumped into the log. We kill the log again, and then we magically see only those sections, only those classes and methods which are responsible for the process of the password on the login screen, which is a very nice thing because we don't have to manually look for those methods and those classes, and that's one of the main things. That's one of the main advantages, which we don't have to fight with that massive undocumented, obfuscated code base. The relevant code sections just magically highlight themselves in the code, in the system logs. So let's go deep how this thing works on the inside, and this is the point where I hand over to Gergő.
Okay, I'd also like to welcome everybody. As Zsombor already mentioned, I'm an intern, so I did the best part of this run-of-the-mill job. I still have nightmares with obfuscated Java, but according to my therapist, I'm on the way to recovery. So I was well motivated to do the magic here, and we dig into that a bit. A little bit about Smali. Smali is the bytecode, or bytecode representation of the bytecode of Dalvik. It's, I don't know if you know, it's a register-based virtual machine. There is basically two types of registers that are eventually the same, but we use a different kind of representation for them. One is for the local variables, v0, v1, and so on. And there is also one for the parameters, which is p0, p1, and so on. In the end, if there is n local variables, then p0 is practically vn, so it's just a good representation to read it easier. There's also two range of registers. The first 15 registers can be used in a lot of cases where over 15 can't. A lot of operation code doesn't work with registers over 15, so they had to be handled differently. Methods are referenced the following way, so class name and the name of the function. And here's a simple Smali snippet. It's a definition of a small function. The first line states that it's a method definition start. It's a public static function. The name is log the string. The parameter list contains only one parameter, which is a string that's going to be represented as p0 later on in the code, and its return value is void. That's the little way in the end. The first line in the method, the .locals, that determines the number of local registers in the code. As you can see, here is only, oh, thanks. So here's only one local register, that is v0 later there. And what we do in this code is basically we put a string here in v0, and then we call the Android log utility with v0 and p0. So basically we write it in the log. And it's also like to pinpoint the last line, which is a return line. Every method exit points are return lines. Okay, so as I mentioned, there's a lot of problem with registers because they had to be handled differently. And the problem is that the operation code for invoke cannot work with registers over 15. So you cannot pass these registers to it. So if you want to log these parameters, then you had to do some magic to arrange that, because the red zone is forbidden for invoke. Okay, so in an ideal world, we would have enough space for another local register. So we just increase the .local line, and that's all. We can use that as a temporary storage for the log tag, and everything is peachy. But we don't live in an ideal world. Otherwise, there would be no obfuscation at all. So in a lot of cases, we cannot increase the local variables because we might shift some register from the green zone to the red zone. In this example, there is only one local register in the beginning. And so parameter 15 is still in the green zone, but after we increase the local, it's going to be shifted to v16. And that means that all the opcodes in the original method will be tainted by this shift because they can't work with that kind of that type of register. So we came up with two different approaches to solve this problem. And the first one was to at the beginning of any method, all the local registers are still initialized. So if we override them, we don't cause any harm in the whole process of the method, because they eventually going to be overwritten by the original code. So the only thing we do, we copy the parameters back to local registers and store in that. And in that way, we can use v0 as the temporary storage for the log tag, and v1 as the temporary storage for given parameters. And then we can use this to invoke the log method. Unfortunately, in many cases, that's not an option. For example, if you are in the middle of the method, so for example, at a return line, then you can't overwrite registers because they eventually going to be used in some cases, and that would taint the application. So, if there is no local parameter for storing these bad behaving registers, then we can use invoke-range opcode, which is also used to invoke methods. The difference is that invoke-range expects not registers, but register range, like from v0 to v5 and all of them. And we can use that over 15. So you can invoke something with invoke-range with v17, which is a good thing. The problem is that if you want to store the log tag in the same method, then the two parameters, two registers have to be next to each other. They have to be neighbors, because you can't pass it any other way. And that's obviously not possible. So what we did, we created a specific method for each parameter in each method for each class. And these specific methods already contained the log tag, like hardwired. And we only had to invoke the specific invoke, and everything is peachy. Unfortunately, Dalvik has an interesting feature. There is an upper limit to methods in a given application, which seems to be a big number, because it's 65,000, but it's not. If you imagine only an application where there's 8,000 methods, average 5 parameters and 4 return line, which is not so extreme in a Smali, then it's already reached. I think my worst case scenario was like 160,000 methods created by this method. So that can't be work. Then if none of it works, then why not use both? So what we basically do, whenever we can do the ideal word method, so just increase the locals, then we increase it, and everything is just peachy. If that's not possible, then we move it. That's only can be used in the beginning of methods. And even if that fails, then there is the invoke-range approach. This results in a slight increase in the number of methods, but it's not so bad. So eventually this whole thing is working as we expected. And here is a small representation of what's going really during change. So as you may or may not see, this is a small public static function which is named sum. It receives 2 integers and returns an integer. It's basically what it does. There is only one local register, v0. It puts P0 and P1, the sum of P0 and P1 to v0 and returns v0. So it's just gets back the sum of the 2 integers. And what our tool does is first we increase the local registers as much as possible. Then we use v0 at the beginning. We can use v0. We put the log string there, and then we use p0, so the first parameter, and this text to invoke the logging method. So basically, whenever the function is called, we just put the parameter with the log tag to the system log. At the beginning, we use v13 because that wasn't in the code originally. So if you change that don't cause any harm in the application. And then we use v13 and v0, which is the return value here, to log the return value of the method. And how does it look like in the system log? There is three types of output log. Everything starts with DL, which stands for deLogger. M is for method, and S for start. So this is the beginning of a method. The first line here is the name of the class, which contains this method. The second line is the name of the method. There is the parameter list, which is an integer in this case, and this is the return type, which is a float in this case. The third line is basically says that this is the first parameter of this function. This line shows that it's an integer, and the last part is the value in this specific case we logged it, which is 800. There is another one, which is DLM-E, which is states for end. So this is the beginning of, this is the end of a method. There's still the name of the class, the name of the function, and this line states that this is the first return line in the Smali representation, and this is the return value here. And the last one is DLM-I, which is for invoke. This is a bit more complex. So this is the monitored class, the monitored method, which invokes the method of the following class, and the method name is this, and the return value is an object, which is Android util display matrix. And in this log types is really easy to follow because there is always a start of a method, between there is some invokes, and at the end there is an end of it. And so it's a really well-structured output in the system log. And with that, I think Zsombor is going to show some demo.
Okay. Yeah. So whenever we analyze the output of our tool, we handle with our. Oh, there's a question.
Yeah, just one question. So what happens if the argument is a string?
Argument is a string. We can dump that string also. Like we have a couple of types which we support natively, like string, long, double, integer.
Well, basically all the primitive types, like long, integer, double, is already implemented. I also implemented strings, which is not so hard, byte array and string array, also intent, Android intents. But in other cases where there is an object, we just state that it's not implemented because using the toString of the method of the object could cause a serious problem in the whole system because it's yeah, recursion. Thanks.
Okay, so whenever we deal with the output of our tool, we see all these three kinds of lines alternating, and we can see and we can reconstruct a very nice flow of the data within the application, and that makes it very easy to analyze and to pinpoint and highlight interesting stuff, which is very important for us when analyzing an Android application, and to see where security relevant bits are implemented. So I think it's time for a demo. We have plenty of time, so let's go for I think I show you. Still have it here. Can you guys see what's on the phone? So we have a very nice application, which is a very simple one. I fire it up. What it does is it literally took like 30 lines of Java code to implement. So it takes a couple of it takes strings, a couple of characters, and when I say encrypt, then it does some AES encryption of the string above with a wording code. So that's a wording key. So that's a very, very easy application. And for demonstration purposes, it's going to be perfect. So let's see it here. Okay, now. So this is we use the one of the example Android applications. That's hence the name. So what I'm going to do here is to first use our tool to change the code. It's going to be automatic. It takes three arguments. One is for the input APK. The other one is obviously for the output APK. And our application and the script does a lot of temporary files like the Dalvik, the APK tool output will be stored in this particular folder, just in case we need it later on. And it does its job. If anyone who's familiar with APK tool, this is like these tools are chained together, just like the. I'll try to find that figure. Just like here. So this APK tool is run first, and our tool is then chained on the output. And we use APK tool again, but to build another APK, and jar signer is used to design the whole thing. Of course, we need a couple of other prerequisites, like we need to have proper key store, which can be used to sign Android applications. But once we have that, the entire process is totally transparent. We don't need to do anything with it. So let's get back to. That's back here. This is the bits of the APK tool again, and jar signer. And once we have a look at the contents, we see there's this example out APK. I remove this one from the phone. Once we have it again, I'm trying to move things so you can see what's going on. Okay, and we kill the lock first. No. So because I'm using this grep command because it's going to be a lot of output, and each line will start with DLM. As you will see, so I fire it up, and there you see, and when I type in something, these A's, say encrypt, and you saw that this is the output. The actual contents of the screen is not very interesting anymore, so let's see what's going on. So we see that there is this, try to make it a little bit smaller. You guys still can read it. Is it still readable? Okay, so there is this line which says that we invoke the encrypt function with 2 parameters. Yeah, this is it. These are the 2 lines which describe exactly what we need. So this 61, 61, 61 line is my A's in the encryption routine, and the other one is the encryption key. And the whole point is, I know at this point the name of the encryptor function, I know the object that contains that function, and I know how it's done. And if I go on, I see that we define a secret key. We use the Java crypto cipher suite to do the actual encryption. And then it returns, this method end returns with an encrypted version of the string. And the whole point is that I didn't have to do anything but using your tool, and didn't have to manually inspect the code itself. And this is, of course, this is a very easy example. It consists of one activity with 1 or 2 functions, so that's pretty easy to follow, even if we look at it with mcedit. But this makes it much easier to follow when it comes to a much, much bigger application. And we come to our second demo, which is this application, this secret. It's an open source, the secret space encryptor application. It can be downloaded from the App Store or the Play Store. And it's open source, so it's pretty easy to check all results against the actual source it was compiled from. So let's see how this works in this much, much complicated case. We have the, no. This is the actual APK. I can have it from the App Store directly or get it from the phone itself. It makes not a difference. So what we do here is we simply use the same application again. As you can see, it takes a little bit longer because this is a much, much bigger application with much bigger code base. And there we have another instance of the app. We simply install it. I remove it from the phone. Then we have it. We kill. So if you fire it up, you see lots and lots and lots of outputs, and this is the way it goes. So I'm not going to dig much deeper into this particular application, but the idea is the same as we saw earlier in that skeleton application, which was much easier to comprehend. And this application, this tool, it gives us a lot of opportunity and a lot of things that can be improved on. So first of all, we took a look at the actual output. So we thought, okay, how can we make this more convenient to use? Because this is very nice, but it would be awesome if we had some much nicer representation of this output. And we came up with another module, so to speak, which converts this whole thing into a very nice HTML output. And if we use JDGUI to decompile the application and to get a Java code, then we can somehow assign the two, and I will show you how this thing works. So first, we need JDGUI, but I have it here. How many of you have used JDGUI? This is a Java decompiler tool. Oh, quite a few people, good. So you know what I'm doing. I look for no, and it need to convert this to jar first. Okay, now I can use JDGUI to get the jar file. And what I do is I simply save all sources to, not here, but here. And what we're going to do now is I simply concat the contents of the log. Okay, we have a nice, it's massive, but it's still there. And what we do now is okay, and if we come here to, where am I? It takes a while to parse it. Maybe I choose a little bit too much of input because it's a massive HTML file. Yeah, it's 2.3 megs. Okay, but it's still comprehended. So we see the same output, but in a much nicer format. I try to zoom in. So it's the same kind of representation as the same kind of structure you saw in the slides. And the cool thing is, when I click it, I can have the Java source itself based on the JDGUI output. And this can come very handy when it comes to analyzing a massive Android application. And I think, come back to the slides. I think that's all. You can find the tool on this GitHub page. It's pretty new. It's just being pushed on. Just feel free to check out, feel free to test, and feel free to comment. And I think we have a couple of more minutes. So if you have questions, just shoot. There's one question. Speak up. So the question was, do we log also multi-threaded applications?
Well, in the original, so the basic Android log contains the thread ID, as you see after. I just go back there. You see, in the first line there is the thread ID, the long number. Where's the? It's right there. But the problem is that the synchronized block sometimes mess up the. So we mess up the synchronized block with our tool. So in many cases with synchronized block we run into a verifier error, and the whole application crashes there. We're still about to solve that problem. I hope we come up with something.
And just to handle these kind of cases, we made like a blacklist about like those objects and those methods we don't want to mess up with. And from a tester's point of view, this is perfectly workable. So you try to process the application, you fire it up, see it crashes, you see the struct trace where it crashed, and you just blacklist that particular object just to see where the rest is going. Another question? Okay, so I think that's it. Thank you guys for your attention.